Hi, my name is Rachel Sue. I'm a senior in mechanical engineering, and for my honors capstone, I decided to continue working with an MHIL project team that I've worked on since freshman year called the Neonatal Asphyxia project. So, to provide some background information on what neonatal asphyxia is, it's a medical condition that's caused by a lack of oxygen before, during, and after birth. There is a variety of different possible reasons for that to happen, but some of them can include a detached umbilical cord or placenta, a long and/or difficult delivery, and improper airway formation during development. The end result is that the oxygen deprivation causes the death of cells in the brain, which then causes impaired brain activity, long-term brain damage and disability, and in the most severe cases, death. Worldwide, neonatal asphyxia causes nearly 1 million neonatal deaths annually, and is also associated with a large number of stillbirths that occur during the labor and delivery process. The number of fatal cases is especially high in low-resource communities, and in India, where our community partner is located, complications associated with neonatal asphyxia cause around 42% of neonatal deaths yearly. So, the primary treatment for neonatal asphyxia is hypothermia therapy, in which the infant is cooled to a body temperature of between 33 and 34 degrees Celsius, and then maintained in that hypothermic state for about 72 hours. This is because even though the lack of oxygen itself causes cell death in the brain, a greater amount of damage actually occurs during a process called reperfusion, which is when the restoration of oxygen to the brain causes the release of harmful chemicals that cause more cell destruction. By keeping the patient's temperature low, the spread of these chemicals is kept to a minimum, and so it allows the surrounding cells to recover, which reduces the severity of the injury and helps reduce permanent brain damage. Our team is currently partnered with Drs. B and Dr. Hina Patel, who are a husband and wife clinician team that run the Hasia Care Clinic, which is based in northern Gujarat, India. They treat a large number of neonatal asphyxia patients, and currently the way that they apply hypothermia therapy is by freezing hospital gloves filled with water and then switching them out periodically. Now, this is a really time and labor-intensive process for caretakers, and so they're looking for a more efficient method of applying hypothermia therapy. Most of the products that are used in the US have automated temperature regulation, and so they require minimal direct intervention from doctors besides at the beginning and the end. But these devices are usually extremely expensive, with certain gold standard devices like the Ticotherm Neo costing in the tens of thousands of dollars, so they're not very accessible to low-resource communities. So in order to address the needs of our community partner and communities with similar needs, the goal of our team is to design and manufacture a device that safely and effectively applies hypothermia therapy to effectively mitigate the brain injury caused by neonatal asphyxia in underserved communities. Based on conversations with our community partners and our clinician contacts in the US, we were able to come up with a list of user requirements and design specifications for our device. So the first is that it needs to be able to effectively apply hypothermia therapy. So it has to cool the patient's body temperature, the target range, within 6 hours, and then maintain it there for about 72. It also should accommodate 95% of infant lengths and weights, and cost less than $750 in order to be cheaper than most other competitive products, require less than 2 hours of training to use, and be able to fit into the oval-shaped trays that they have at the care clinic, with access dimensions of 60 and 75 centimeters. The material that's used should be comfortable for the patient so it doesn't cause pain and sores, and it should also be reusable, easily cleanable, and puncture resistant. Aesthetically, there should be an appearance that doesn't cause any undue concern for the parents of the patient. So, to address these requirements and specifications, our team has come up with two primary concepts, both of which function on this premise of an Arduino-controlled water loop that circulates room temperature water to lower the patient's body temperature. So the patient will lie on top of the patient interface component, and water is pumped beneath them through the patient interface to draw the heat away. The water is then pumped through the radiator, where fans are used to convectively bring the temperature back to equilibrium at room temperature, and then send the water back to the pump. So throughout this process, the Arduino system is constantly reading the patient's temperature using a thermal probe, and then adjusting the fan and the pump speed accordingly to adjust the rate of heat transfer. So our team is currently exploring two different possibilities for the patient interface portion, one of which is this waterbed design, which is made of a heat-sealable nylon covering that's filled with water and that serves as a mattress, and it has an inlet and an outlet for water circulation. So on the left, there's a CAD model of the design with this brown block indicating where the patient would lie on the mattress. On the right, there's a more realistic water bladder. This is sold online and something that we're planning to use for some of our preliminary testing. So the main advantage to this design is that it maximizes cooling surface area, since the patient's entire back would be in contact with the mattress. There's also fewer layers of insulation in this design between the infant and the mattress, as compared to our other design, which I'll describe a little bit later. But some of the disadvantages to this design include that, as you can see in the image on the right, water bladders have a tendency to form a curve rather than a flat surface. So we'd have to take some extra design considerations to make the surface more flat and eliminate any risk of the infant rolling or sliding off the surface. This design as currently planned also requires a pretty large volume of water, which could make it pretty heavy and inconvenient to move around when it's filled all the way. So we had originally planned to build a medium fidelity prototype of this design this semester, and so we'd practiced heat sealing and done research into possible joints in preparation for it. But due to the situation around COVID-19 and online classes, we had to push the prototyping into next semester. The second patient interface design we were looking at was a tube bed that's made of a hard plastic manifold through which the water runs in parallel channels. To make it more comfortable, a foam layer would be added to provide some padding, and so it's cleanable. The device would be enveloped in a heat-sealed nylon cover, similar to the waterbed. Some advantages of this design include a more even temperature distribution because the water is flowing evenly through all the channels, and there's a lower required volume of water than with the waterbed design. However, the cooling surface area is smaller for this design because the patient would only be in contact with the top of the cylindrical portions instead of an entirely flat surface, and the foam that's required to keep it comfortable for the patient would make extra insulation and impede the heat transfer. Now, similarly to the previous design, we had also planned to prototype this one this semester, but we're not able to do so. So after discussing a few possible ideas for the patient interface, there's also the question of how we plan to develop the Arduino control system. So on the left is shown a diagram that shows the cooling curve from the Secotherm Neo, which is considered the gold standard of hypothermia therapy devices in the US. So our goal for our device is to emulate this cooling curve as closely as possible, so cooling down to target temperatures within 6 hours, and then maintaining the steady temperature with minimal variation for the next 72, before going into a rewarming phase for about 12. So in order to accomplish this, our team is exploring the use of proportional integral control for the feedback system. So through the user interface, the doctor would input a target temperature, and the Arduino would be constantly measuring a temperature from the temperature probe that'd be with the patient. And so based on the calculated error between the measured and the target temperature, the Arduino then performs calculations to determine how it's going to change the pulse width modulation signal to the pump and the fan to change the speed and rate of heat transfer to better achieve the target temperature. So initially we'd thought about using PID, proportional integral derivative control, but based on input from one of our mentors, it was decided that the rate of temperature change is so low that there's not much concern about overshoot, and so it would be simpler to program, but still effective to neglect the differential term and just focus on the PI portion. Due to the situation this semester, our team wasn't able to accomplish all of the things that we initially set out to. Instead, we spent more time focused on a lot of theoretical considerations, which we hope will be as helpful to us in the future as we had hoped that our hands-on prototyping and testing would have been. So in the future, we hope to build and test our prototypes of the two patient interface designs, determine the proper algorithm for adjusting fan and pump speed based on temperature error, and reschedule our plans to visit our community partners. In terms of additional topics to look into in the future, our current system doesn't include the capability for rewarming by itself. So in the future, once the cooling loop is settled, perhaps there'll be more time to look into that aspect. Thanks so much for listening, and feel free to leave any questions or comments that you might have.